And we're live. Hi. Good. Hello, everyone. Thank you for coming along to yet another Angular London meetup. I think this is our 6th one since the beginning of the summer, which is fantastic. We were a bit quiet for about a year or so, but we've come back in full force, and we're just getting talk after talk, which is fantastic. I've pushed Josh out into the back room today, and I've taken over. So we're going to have lots of fun today. And I'd like to introduce, joining me today is Joost. He is one of our amazing collaborators on the Angular team. And he's a full member of the team and has been working on it for a few years. And he does some amazing work in the compiler areas. And I've had lots of fun working with Joost over the last year or so, because we've been heavily involved in things like ngcc together. And it's always a delight to dig through his brains and get his feedback on my pull requests, because there's always lots of really powerful technical stuff going on in there. So hello, Joost, how are you today?
Yeah, I'm doing great. Excited to be presenting this night here.
Excellent. Yeah, this is going to be technical night tonight, because Joost is going to tell us some deep magic inside how to find memory issues in your applications. And it blew my mind when he found this bug, and we spent ages looking at it going, oh, that's so difficult to pick up. So this will be a really useful thing for everyone to know about, I think. So just to let you know, there's if you're watching this on YouTube or Facebook, you can put comments in the streams there, and any questions that you have, please ask them during the talk, and I will pass them on to Joost at the end of his talk. So we'll have a little Q&A period at the end where I'll make sure he answers all of your questions, and then shortly after that, we will be going to a kind of a networking session, as we've done before. This time, instead of Zoom, we're actually going to be using Google Meet. And there's the link coming up. Josh is working hard in the background, so you can either try and copy that down, or we will post it into the stream comments later on. And you'd be most welcome to join Joost and Josh and me in that meetup later on to have a bit of networking chat, which is always a nice way to finish off the evening. We've been really lucky with the speakers that we've had over the summer, and we're always looking for some more. So if anyone out there who's watching has something interesting they'd like to talk about, then we'd love to get you online. So do get in touch. Anyway, without further ado, I think we'll hand over to Joost and let him get started. I think you're going to bring up your talk, or Josh is going to bring it up for you, and then I'll get out the way and leave you to take over the reins. Thanks very much, Joost.
Yeah. All right. So welcome, everyone. I'll be talking about the tail of memory leak in the Angular compiler. I mentioned my Twitter handle here, but I'm not very active on Twitter. So, feel free to either look at it or not. A bit of information about myself. I work at Bluerig in the Netherlands by day, but I'm also contributing to Angular quite a bit, and I've been part of the team for 1 to 2 years now, I think. I live in Utrecht, which is in the Netherlands, and it's famous for the Dom Tower, which is shown on the right. But at the moment, it's not like or not unlike the Big Ben, because, well, this is what it looks like as of last year. They are currently busy renovating it. So it's a bit like London's Big Ben. Yeah. So Pete already mentioned it in the introduction, but I've been part of or following Angular development since Ivy started in late 2017, and I'm quite fascinated about compilers. So that's how I got into the ngcc development, which is the compatibility compiler. And along the line, my kind of efforts have expanded into also the main Ivy compiler, particularly its type checker for templates. That's one of my favorite areas. And as Pete mentioned, we are working closely together, and currently we're actually looking into replacing ngcc with a new effort that we call the Angular linker. But I won't go into that tonight because we won't have the time for it. All right. So at the beginning of this year, or actually it was June, I see here in the GitHub issue, there was a report on GitHub that users ran into memory issues a couple times a day, where if they ran ngserver in watch mode, it would basically crash, well, for some users every few iterations, and for other users every couple hours, but still it was quite prevalent, and well, we needed to look into that and try to see what was going on. And although we were able to quickly identify the culprit, we also kind of analyzed the problem more deeply, and then found some interesting things about how JavaScript engines deal with memory, etc. And today I will be showing you kind of the same analysis that we did a couple months ago to kind of reveal what was going on. But before we do, let's first actually look into just general debugging of Node.js, because we need a debugger to look into the memory profile. And well, the most straightforward way maybe is to run Node itself. So you have to run the Node binary itself. And that allows you to pass additional flags to Node.js, namely the inspect-brk flag. BRK means break. And in this instance, that means that you will start Node.js, but it won't actually start running immediately. And this allows you to first attach a debugger to that process and only then start running your application, because otherwise you run the risk of your program already finishing before you're even able to attach. So there's also -- inspect, but I typically only use -- inspect break. Then once Node.js is running and stopped, basically you can go into Chrome -- inspect, and it brings up a page where it should have a button that says Open Dedicated DevTools for Node. And if you click it, then you should go into a DevTools screen that you're used to from, well, the regular web inspector, basically. Only now it's targeting your Node.js application that you ran from the command line. Alternatively, there is a tool from the Chrome team. It's called NDB for Node Debugger. And it basically offers an integrated debugging environment for Node.js. It is built also, or derived at least, from the web inspector, so kind of the same UI as you're used to from Chrome. But it has some neat features, like being able to debug into multi-processes. So, for instance, the compiler will have several sub or child processes, and NDB will also help you debug those. And other than that, it's also kind of handy to have full access to the file system in this tool. One downside, though, is that it's not really well maintained at the moment. So I believe the last release is from only about a year ago. And that also means that it ships with an older version of Chrome, which is 73. Well, we are currently at Chrome 80, I believe. But you can use this as an alternative, which might sometimes be easier to use compared to using the web inspector from Chrome itself. And NDB is fairly easy to use. You just well, install it globally on your system and then prepend the NDB binary to run the same process as you would before. So you could just run ndb ngserve, for instance, and then it would run ngserve in the debugger. All right, so I'm doing this with NDB, so I screenshotted all of the steps I took, and we'll end up in the sources step when we started. And here you can see how it's initially just in the paused state, because that's how it starts. And then we first need to press kind of the continue button to get it all started. And because we're kind of interested in debugging the memory, we can just run a single compile and don't bother about it. Because after the initial compile is completed, then we need to look into gathering the memory heap. So once it's complete, you can switch to the memory tab. And you will see here a couple of processes that are available for creating a snapshot from. And the snapshot allows you to see kind of the state of what was inside of the JavaScript engine at the moment you captured the snapshot. And this allows you to basically drill down into all of the various JavaScript objects that are available. So in our case, we select the main process. You can see here in the list, there is the ngserve process and also the type checker worker. That's something that the CLI spawns in the background to run the template type checking, but we're mainly interested in the main process. So we select the main process and then click take a snapshot, which you can do from this button right here. Also, as a tip before you do so, it might be a good idea to first press this garbage can first, because that will actually force a garbage collection to run, and that helps in looking into snapshots that maybe still have objects that you didn't expect there to be, whereas they would have been garbage collected if you would have pressed this button first. So I mostly forget to do that, but it's a nice recommendation to actually do it that way. So creating the snapshot may take a couple minutes sometimes. I've seen cases where it even took 40 minutes, and then you're waiting and waiting and waiting, hoping for it to complete. In general, the smaller snapshots or the fewer, the less amount of memory you have, it's mostly takes only a couple of seconds or minutes. And then you start to see this screen, and it shows you all of the memory that is allocated based on the type of object. So in this screenshot, you see there is a lot of strings. We have 113 megabytes of strings allocated into the memory. This basically allows to see the various objects in memory and inspect what's going on. The columns on the right show kind of the memory usage of these objects. The shallow size indicates the number of bytes that the objects themselves take in the memory, whereas the retain size is kind of the total number of bytes that is reachable from this kind of instance. That doesn't necessarily mean that seeing a large retain size means that that's also kind of where a leak occurs. So it's sometimes hard to look at only those numbers and actually derive some information from that. So be aware of that. What you can do in the list at the top is expand the type of object you are interested in, and then you get all of the individual instances associated with that type. And you can drill down the memory that way, following all of the references into the objects that it refers to. And be aware that sometimes you see here stuff that you are not familiar with. because it will also show you like the internal JavaScript engine bookkeeping structures that are somewhere hidden inside of the virtual machine. What's also neat to know is there is this number associated with each instance. And especially when debugging a memory leak, it's kind of nice to be able to refer to this number as being the unique identifier of an instance, because that helps into kind of comparing the various instances that you will see in maybe a new snapshot that you take sometime later. You can see which of the instances correspond with the earlier snapshots you made. Then we transition into the bottom panel, and I have an instance selected here. And once you do that, you will get additional data in the retainers panel at the bottom. And it's basically the path to the object, or yeah, so the various paths that reach into that object through some other instances. And this is especially useful when debugging the memory leak we are currently looking at, because somewhere in here there's some kind of a reference that we didn't expect, and we should get rid of that reference in order to fix the memory leak. And actually finding this spot is, of course, where the fun begins, because then you have to be kind of familiar with the structure and infer kind of to what extent you expect it to look like that, and at some point you no longer expect it to look like that, because that's an interesting point to then figure out why it's happening as such. So in this case, it actually means that I will show you a bit about how the compiler works, because that helps in kind of looking at these at the memory dump and inferring where it goes wrong. So at the heart of the compiler is the ngcompiler class, which is responsible for driving a single compilation from start to finish. So you give it a couple of source files or your tsconfig, and this happens from within the CLI, of course. And it is responsible for, well, basically driving the regular TypeScript compile, but also on top of that, add the Angular behavior, because we also want to recognize all of the decorators, for instance, and do template type checking, etc. The ngcompiler isn't particularly smart of it by itself. It delegates into various subsystems to actually do the work. But at least it's responsible for creating all of these subsystems according to the compiler options that are configured. So for instance, this is the template type checker, or the dependency graph of all of the files that reference each other. It will also set up the JavaScript emit transform, which is responsible for inserting the AUT compiled code into the JavaScript the TypeScript eventually generates. And I want to emphasize here the Angular decorator recognition, because that's delegated to the trait compiler. And the trait compiler is kind of the central bookkeeping place for the Angular decorators that you have in your program. It scans all of the source files on disk, basically. And whenever it finds an Angular decorator, it will register a so-called trait. And you should think of a trait as being a representation for that declarator, but it captures some more information so that the compiler can use that information to drive the AOT compilation phase. And there's distinction in kind of the information that is gathered here in the trait compiler, namely the data that is independent from other decorators. This is what we call the analysis data of the decorator. And alternatively, there's also the resolution data of the decorator. And this pertains to the information that is crossing multiple decorators. So for instance, the relation between ng modules and the components is resolution data. And the resolution data is only gathered after all of the analysis data has been gathered as well. So there's a kind of a two-phase approach to that. For example, to look further into the analysis data, one thing would be the parsed template that, for instance, a component has. And now you see how incremental builds might benefit from reusing some of that data, because it would be wasteful to, well, basically reparse all of the templates during every compilation if you only changed a single template, for instance. So this is where the incremental rebuild architecture comes into play. So let's go there. Where we have some incremental build strategy that allows a previous compilation result to be captured and to be reused in the next compilation. And the incremental driver is responsible for determining which of that information is actually safe to carry over. So you can imagine that, for instance, the analysis data of a previous compile can be reused for, well, maybe 99% if I only changed a single template. And the incremental driver will figure this out depending on the changes that you made. The incremental driver will actually reference the trait compiler, because the trait compiler contains all of the analysis data and the incremental driver is able to reuse this data. So that's why it refers to that trait compiler in order to reach into that data. So to look at the kind of the object graph that we would expect to see in the memory snapshot, we start at the ng compiler at the top. It references the incremental build strategy, and then it started from only having the previous incremental driver available, which has the trait compiler as its state. And then when we start a new incremental compilation, or when we finish this compilation actually, we will have prepared a new incremental driver that is fully up to date with the trait compiler of the compilation that was just completed. And at this point, we extend the incremental build strategy to set a next pointer. And that's how we now have two incremental drivers and two trait compilers. So what happens next is when we start yet another incremental compilation, we will use the incremental build strategy to basically replace the previous pointer with the next pointer, and then start out with basically this situation again, where next has been replaced, or well, next is now yet again missing, and previous is the one that was the next as it was here. And that also means that at that point, we should have been able to no longer reference the old trait compiler. So this whole subtree should have been gone. And that's why, in theory, there shouldn't be a memory leak here. But actually, we did have a memory leak. So at this point, we are kind of looking into why or where that memory leak occurs. And this is where we go back into the memory debugger. But with this additional information, we should now be able to better understand what we're looking at in the debugger. And I made two snapshots here. The first snapshot was after the initial compile had completed. And the second snapshot is just after we changed some template and therefore an incremental build had ran. And I searched for ngcompiler, which you can do through this search box. And it will only show or filter down the instances based on the name you're searching for. And in this case, it's all as expected. We have this ngcompiler instance, and you can see how it's reachable from the Angular compiler program or plugin that's set up in the CLI. And this makes perfect sense. But then looking at the second snapshot, which is after the incremental compilation had completed, we'll actually see two ngcompilers. Well, there is this new one, which is this number, and it shows the exact same path as the previous compilation. So that's also as we expect. But you can see here how, well, the ngcompiler from the previous, that was 619569, is still available here, 619569. So somehow we are retaining that ngcompiler instance, but it shouldn't be there. So if we activate it, it will show a retention path as well in the bottom panel. And well, this starts to look a lot different from the one that we expect. So this is what we expect, whereas this was what we actually got. And that doesn't look at all what we expected. And this actually shows how the problem originates, or where the memory leak got introduced. So if you look at it more closely, we'll start looking at the bottom, and you will find basically the graph that I showed in the previous slides, only now in the memory dump. So we start from the previous, which retains the incremental driver, and the incremental driver will then retain the trait compiler. So that's expected. But somehow there's also this path that ends up referencing _this. And because we had selected the ngcompiler, we know that this is ngcompiler. So somehow this path is creating the leak, and we need to figure out how this path is created. So this is the theory as we expected it, but what we're observing now is somehow from the trait compiler there is some path that retains now this instance of ngcompiler. And you now start to see the issue where, well, this is an ngcompiler which holds on to all of this, but we also have an ngcompiler right here. And this one will basically be a repetition of this slide, where it also, of course, has an incremental pointer to the incremental build strategy, and, well, it will then retain all of the prior compilations. And now we start to see how this is kind of a severe memory leak. And that explains why people saw their ngserve processes crashing all day. So based on what we just saw in the memory debugger, we need to kind of figure out where the memory leak originates. And what we know is that we noticed the _this pointer that was retained at the top. So we start looking into the constructor of ngcompiler, because that is where the _this pointer is declared. And if you look at the code there, you see how we set up a module resolution cache. And it has this closure associated with it. And in the retainer path that we saw in the memory debugger, we also noticed that it was associated to the module resolver. So this is likely the culprit of what's going on. So we thought, all right, that this uses like the this.adapter. But adapter is also like a constructor parameter, so our guess was that we would just replace this adapter with just adapter, and that would no longer, so that we would no longer refer to the this pointer here, in order to allow all of the this and therefore ng compiler to no longer be referenced. So that's the change we made, and then we looked into the memory debugger a second time, and we saw this. And I was debugging this late at night with Alex Rickabaugh, and we were like, what's going on now? This is still the same issue. So we checked if we actually were changing the file that was actually running. And then we tried rerunning it again just to make sure it was really going on like this. But it turned out that it was indeed still leaking. So now apparently we made this change to this closure, but we still see that there's a retention path from the trait compiler to the ng compiler. So our problem is still there. And we were quite confused at this point. But then we looked at the ng compiler constructor again. And this is what we noticed. Another closure in the same scope that also references this dot adapter. And now it started to become clear that having these two closures in the same lexical scope, namely the ng compiler constructor, would share a single closure scope for all of these. So the fact that we just replaced the first one and got rid of the this adapter and replaced it with adapter didn't actually fix it, because there's another closure that still references this. So the this pointer still needs to be retained. And that's how we still have the memory leak. So to illustrate this a bit better, we started to reproduce this in a smaller scenario. So this is something you can run from the Chrome console or from StackBlitz or whatever you want. And it's basically the same pattern, only to figure out what's going on a bit better. So this is an immediately invoked function expression to illustrate kind of the same structure that the constructor used to be. And we set the underscore this pointer to, well, exactly what it would have been in the constructor as well. Then we assign two variables. They are both local variables, and they are assigned into the this pointer as well. So we end up with an object with properties A and B. And there's two functions where getA returns the local variable A, and getA underscore this returns the same value, but now read from the underscore this variable. And we can log those functions into the console. And you can then look in the console and expand into the scopes property, because that tells you kind of the closure scopes that are captured in order to reach into the variables that are needed in that function. And in this case, we see, well, A is there, of course, because we need A here, otherwise it wouldn't be available. But you also notice how underscore this is available, whereas this function doesn't depend on underscore this. But you start to see how we retain all of it. So we do have A and we also have B, but B is never used. So this would actually mean that we would retain into the memory of B, even though it's not used outside of any of this. And then if we also look at the log of getA underscore this, it's basically exactly the same. Because this closure state is identical to the previous one. And that's why getA also has the underscore this variable in its closure state, because the V8 JavaScript engine creates such a closure scope well, only once within a single lexical environment, which is in this case the immediately invoked function expression. So just to show what happens if we were to remove the getAthis function and only have the function that does no longer reference _this, then we start to see a closure scope of that function that only captures the local variable. And now you see that the _this pointer is gone. So what we needed to do in order to fix our memory leak was basically to get into this situation where we had only a single, or where we would no longer retain the _this variable in the closure scope of that callback function. So looking into the code again, we started with this, and we observed how in this case we could just replace it with about function. So that's what we changed it to be. Alternatively, we could have created a separate function that will therefore get its own lexical scope and then create the same closure from there. But because that is a smaller lexical scope, we wouldn't undesirably retain the _this pointer in that case. However, in this case, it was all possible with just bind. So that's what our solution was. And then to finalize all of this, because we have now reached the point where it's all no longer leaking. So we have been successful at fixing the leak. And something that was interesting here is that we have these two closures, and the V8 JavaScript engine will only allocate a single closure scope for both of these closures. But something interesting happens in this particular case, because the closure that we pass into the filter function, well, that's called immediately and then no longer used. Whereas the closure that was given to the module resolution cache has a much longer lifecycle because it is retained into the trait compiler, as we saw. So this is an interesting point in terms of kind of how a memory leak can occur, because of the shared global or the shared closure state, it will still have to hold on to all of the memory that was needed into kind of the function that was created here and never used again after that. So if this were to retain all sorts of memory because it needed it to operate, then all of that memory would have also been allocated in this closure scope, which is something which we found interesting, at least. But that's basically the end of the memory leak in the Angular 10 compiler. And you saw how we kind of went about analyzing it, and also how we ended up at solving it in the end. So that's a wrap, and with that, I would like to end it like this.
And I'm back as well. Hello. That was marvelous, Joost. You've gone a little bit dark all of a sudden, maybe because your screen is no longer displaying brightness on you. Or maybe I'm just much brighter than you.
No,
I don't think that's true at all.
I'm 1 hour into the future.
Indeed.
And the future is a bit dark. Well, that's a dark sentence.
So that was, as I said earlier, that was absolutely fantastic bit of debugging. How long did you actually spend trying to uncover that when you're working with Alex? Like, was it an hour or what?
Yeah, so I think we had kind of traced down the point where it all went wrong in half an hour, and then needed yet another half an hour to understand why this was happening, because we were both so confused. So yeah, it was a wild ride, that hour.
It would have been absolutely fascinating to have been like a fly on the wall, watching over the two of you, over the shoulder of the two of you, trying to get your head around this. If anyone on the stream has got any questions about this, I've got plenty, but I don't want to hog the questions. So if any of you who are listening in want to ask any questions, I'll very happily pass them on. One of the questions I had though was, like on the surface, this code looks perfectly normal and sensible and safe, and actually it requires quite a deep understanding of closures and how things get captured to identify it. Do you have any suggestions for people out there as to either anti-patterns to avoid or flags to look for when you're looking through your code that might potentially cause one of these things, so that they can look in their code and say, oh, hold on a minute, like when they're doing a code review, perhaps we shouldn't be doing that, or we need to be careful of that? Is there anything obvious that you would recommend?
Yeah, so I think that this is a very hard bug to be able to avoid, like detecting code reviews even. Because like you said, it's so hard to reason about all of these closures, and they're all over the place in JavaScript, so you won't start analyzing all of it. But I think what I showed in the last slide here is knowing kind of the different life cycles of your closures, and thinking about the fact that the module resolution cache has kind of a long life cycle. So the closure that we pass there will also live for the same life cycle. And maybe that's a point where you need to realize that, well, maybe we are affected by some other closures in scope, because we don't want to retain all of that memory. But I generally think that this is not something that you can avoid just by looking at the code. It's such a convoluted thing to detect.
So it seems to me that lots of these kinds of memory leaks come from using callbacks and passing callbacks around, because obviously the callback will have a closure attached to it. Is this kind of bug an argument for avoiding using callbacks in general, perhaps, and using a more object-oriented approach where you would have objects that are responsible for managing that kind of behavior and passing the objects around rather than the callback? Would that avoid this kind of capturing of the closures?
Yeah, so that would avoid it, because, for instance, a class is typically declared at the top level of a module. So then you're not affected by the lexical scope of some unrelated stuff. But also, I don't think there's generally it's not generally a bad thing to use closures. So I wouldn't consider looking into avoiding them or replacing them with a more object-oriented approach, just to not shoot yourself in the foot every once in 10 years or something.
Yeah, it was a devil's advocate kind of question. One of the real powers of JavaScript, obviously, is that functions are expressions that you can pass around, and that provides a lot of the power of it. But there's often this kind of debate between functional coding and classical object-oriented coding, and perhaps the classicists would claim that this is an argument against it. But
yeah, for me, it's the same as premature performance optimization, right? Where you shouldn't avoid patterns for stuff that you don't know what the effect will be if you don't measure it. And in this case, it needed a bug in order for us to actually start measuring it and look into addressing it like this, which is similar to how you address kind of slow code. Because at the moment it becomes slow, then you start profiling it and investigating what needs to happen to make it faster. And this is kind of the same thing.
Yeah, that's very sensible. I'm definitely not keen on preempting performance issues.
Yeah.
Cool. Well, so we've got this meet that we're kicking off in a couple of minutes. It's up on the screen at the moment. So if any of you who are watching at the moment would like to join us, we're going to move over to there, and then you can have more informal chats and dig into some of maybe what Joost was talking about, or just talk to us in general about Angular. We might even disclose some information about the linker that we've been working on, if you want some secret inside info. But other than that, I think we probably just melted everyone's brain. Certainly, even having seen this bug and talked to Joost about it, and even seen the slides before, I still was like, oh, I've got to work really hard in my brain to try and get my head around this. So it's a real tricky area, but it's definitely a good thing to know about. It's not something I knew about before. So what we'll do is I'd like to say thank you again to Joost for an excellent talk and really, really interesting topic. And if anyone is not joining the meetup, don't forget that we are looking for more speakers. We've got a couple lined up for the end of October and November, but we want to push all the way through to the end of the year, hopefully. So please do get in touch. Otherwise, we'll go and pop over to this meetup now, and hopefully we can have a nice chat and a bit of networking before we finish for the evening. Thanks again to Joost, and thanks to Josh in the background for keeping everything running. Tickety boo. And speak to you all next time. Bye.
Bye all.